Welcome everyone. Today we're jumping right into the mechanical properties of solids. My goal here is simple, to break down the key concepts you absolutely need to know and show you how to use them to crush those questions on your NEET exam. So let's get right into it. What is a solid really? I mean, down at the atomic level? Well, forget thinking of it as just a hard block. It's way cooler than that. Imagine a perfectly ordered grid of tiny balls, and each ball is connected to its neighbors by little springs. Seriously, so when you pull on a solid, you're stretching those springs. When you push, you're compressing them. This one simple idea, this ball and spring model, it's the key to unlocking everything else we're going to talk about. Okay, so here's how we're going to tackle this. First, we'll look at springs and sponges, what solids are really like. Then we'll get into the language of force, then Hooke's law, how to measure stiffness, and finally we'll put it all together for theory to test day. Let's get started. All right, section 1, solids, springs, and sponges. Let's dig into the big idea here, elasticity and plasticity. So what exactly is elasticity? Well, it's basically a material's ability to bounce back, to return to its original shape once you stop pulling or pushing on it. The best way to think about this is like a spectrum, you know? On one end, you've got your perfectly elastic stuff. Think of a quartz fiber. It snaps back perfectly, no questions asked. Then, way over on the other end, you have perfectly plastic materials. Picture a chunk of wet soil or maybe some wax. You squish it and, well, it just stays squished. Now, of course, most things in the real world live somewhere in the middle of this spectrum. Okay, moving on to section 2, the language of force. To really talk about this stuff, like a physicist, we need a couple of new words in our vocabulary. And these two words are absolutely critical, stress and strain. So, what's stress? Well, it's the internal restoring force that pops up inside a material when you mess with it. Remember our little atomic springs? Stress is literally the measure of how hard those springs are fighting back. And how do we calculate it? Simple. It's just the force you apply divided by the area it's applied over. F over A. That's it. All right, so if that's stress, what's strain? Strain is the result. It's the measure of how much the object actually deforms or changes shape. It's a ratio. You just take the change in its dimension, say the change in length, and divide it by the original length. And because it's, for example, meters divided by meters, what happens to the units? They cancel out. So strain has no units. It's a pure number. Okay, this is the big one. If you remember one thing, remember this. Stress is the cause, strain is the effect. I'll say it again. Stress is what you do to the material. Strain is how the material reacts. It's a cause and effect relationship, pure and simple, and it is the foundation for everything we're going to build on. Now, stress can come in a couple of different flavors. Don't let the diagram scare you. It's pretty straightforward. First, you've got normal stress. This is when you pull on something, that's called tensile stress, or when you squash it, which is compressive stress. Then you have shear stress. The best way to picture this is a deck of cards. When you push the top card so it slides over the others, that's shearing. So one is about changing length, the other is about changing shape. All right, section 3, Hooke's law, the golden rule. So we've got our cause, stress, and our effect, strain. The million-dollar question is, how are these two connected? Well, that brings us to probably the most important rule in this whole topic. And here it is, from Robert Hooke himself. Within the elastic limit, stress is directly proportional to strain. This is it. This is the golden rule you have to know for your exam. But there's a catch, right? That little phrase, within the elastic limit. It means this rule only works as long as you don't stretch the material so much that it gets permanently damaged. Go past that limit and all bets are off. Now check out this graph. This is what Hooke's law looks like in action. See that straight highlighted part? That's the elastic region. As stress goes up, strain goes up in a perfectly straight line. They're directly proportional. And the slope of that line, how steep it is, that's a super important number we call the modulus of elasticity, or E. As long as you're in that straight line zone, the material will spring right back. Okay, section 4, measuring material stiffness. So that constant E we just talked about, it's not just some random letter. It's a number that tells you exactly how stiff a material is. Think of it this way. A material with a really high modulus of elasticity is very, very stiff. You have to apply a ton of stress just to get a little bit of strain out of it. But here's a good question. Does one size fit all?
I mean, is measuring stiffness for stretching a wire the same as measuring it for, say, squishing a ball from all sides, or for twisting something? The answer is nope. It turns out we need a different kind of modulus for each different type of deformation.
And for NEET, you need to know these three big ones. First up is Young's modulus, which we call Y. This is your go-to for changes in length. It's the stretchiness modulus. Next is the bulk modulus, or B. This one is all about resistance to changes in volume. Think of it as the squishiness modulus. And finally, we have the shear modulus, eta, which measures resistance to a change in shape. That's your twistiness modulus. And notice the pattern? Each one is just a specific type of stress divided by its matching strain. Okay, let's bring it all home. Section 5, from theory to test day. Enough with the concepts, let's actually apply this stuff to a real NEET-style problem. This is where the rubber meets the road. And just look at this. This is why this stuff matters. We're talking about the real-world design of bridges, buildings, cranes. All of it relies on understanding these material limits. So while we're about to tackle an exam problem, remember that these are the very same principles engineers use every single day. All right, here we go. A classic NEET problem. Listen closely. You've got two wires, steel and brass. They have the same length and the same area. Now, here's the info you're given. The Young's modulus of steel is twice that of brass. The goal? We want to add weights to them so that their lower ends finish at the exact same level, meaning they stretch by the same amount. The question is, what's the ratio of the weights you need? Take a second, maybe even pause, and think about how you would start this. So, what's our game plan? How do we attack a problem like this? It's a simple four-step process. First, what's the key condition the problem gives us? It's that the ends are at the same level, which means their change in length, their delta L, has to be equal. Got it. Second, what formula do we know that has all these variables? Young's modulus, of course. Third, let's rearrange that formula to get what we're looking for, force, by itself. And finally, step 4. We'll set up a ratio comparing the force for steel to the force for brass. Now this is where it gets really simple. Look at our rearranged formula for force. The problem tells us that L, A, and delta L are the same for both wires. So when we compare them in a ratio, all that stuff just cancels out. What are we left with? We're left with the beautiful, simple relationship that the force needed is directly proportional to Young's modulus Y. F is proportional to Y. And we're at the finish line. If the force is proportional to Y, and the problem told us that Y for steel is 2 times Y for brass. What does that mean? It means you need 2 times the force for steel. So the ratio of the weights, steel to brass, has got to be 2 to 1. Boom. Done. And look, this problem is a perfect example of why just memorizing a bunch of formulas for NEET is a bad idea. It's not about memorization. It's about understanding the relationship between the variables. Once you see that F is proportional to Y, the problem solves itself. These formulas are your tools, and practice is how you learn to use them. So there you have it. We went from tiny atomic springs all the way to solving a test question. But it's wild to think that these same principles can explain why mountains on Earth can only get so tall before they collapse under their own weight. The applications are everywhere. So my advice is to keep asking questions, keep practicing, and really dig into these concepts. Good luck out there.